So another important word that we will always talk about is monotone. And it's not really a big deal. It just sounds fancy, but it's really not. Here, I'll give you a quick example of functions that are monotone. If you have a function such as y is equal to the square root of x, and you look at it just on the positive side, you see it's always going up, always increasing. That makes it monotone. It's always increasing. Compare that with something like y is equal to sine of x. This is, sometimes it goes up, sometimes it goes down, sometimes it goes up, sometimes it goes up. This is not always increasing or decreasing. So this would be not monotone, monotone. Okay, you want to see it again? Here, y is equal to 3 over x. So let's just keep it on the positive side. This one is always decreasing. It's always going down, and it has no up and down and up and down. It's one way. The next item here, if I have x is equal to 5 and I have x equal to 6, I guarantee you that 6 will be smaller than the next one, and 7 will be even smaller than the next one, and so on and so forth. Anytime that happens where the next term or the terms to the right are smaller than the terms on the left, that means you're only going one way, either only going down or only going up. So we have things like monotone increasing and monotone decreasing. Of course, we've got a fancy way of saying that too, not just with the pictures with the uphill and downhill. The fancy way of saying that would be that we say that the sequence AN is monotone increasing if and only if the next term, which is the n plus 1 term, is bigger than the previous one. Whoa, I forgot the A. Somebody stole the A here. A. So we say that it's monotone if and only if the next one is bigger than the previous one. For every single number n. That's increasing. And of course you could have decreasing if the next one is always smaller than the previous one. That's it. That's monotone. Of course it gets interesting because sometimes it's not that easy to show that it's monotone, and it's important because a lot of theorems will depend on this property. If a sequence is monotone and increasing, all the magic happens. That's why it's important to know this word. This is an example of something that's clearly, let's see if it's increasing or decreasing. Sometimes you can just make a list here and figure it out. I wonder if we could do that here. Let's look at the list here. For n is equal to 1, you have 1 over 1, 1 over 2, 1 over 3, 1 over 4. What do you think? Is this always decreasing or increasing? Clearly, the numbers are getting smaller as the quotient is growing. Sorry, as the denominator is growing. The quotient is getting smaller, so this would be monotone decreasing. Okay? That was a super easy example, right? Make it look easy. That's why they pay me. Here's another one. What's happening here? Let's just look at it. We can look at it. Let's analyze this in terms of the sequence. So you got first term, when n is equal to 1, you got 5 minus 1 over 1, which is also known as 4. Then you have 5 minus 1 over 2, which is 4.5. Then you have 5 minus 1 over 3, etc., etc. Dot, dot, dot. So this looks like 4.5, 4.6 bar, 4.75, etc., etc. So this would be an example. Look at the numbers 4, 4.5, 4.6. As this number gets smaller, you're subtracting less. So this would be monotone increasing, of course. Monotone increasing. There you go. That's monotone. And of course sometimes it's not that easy to tell whether something is monotone or not, and so sometimes it takes a lot more clever ideas. Hey, you want to see a fancy way to show that this is monotone increasing? What the hell, why not? I'll throw it in this for free. This was not part of the deal, but I'm going to throw it in for free. Suppose you have f of x, which is equal to 3 plus 5 over n, right? F prime of x would be equal to 3 minus 5 over x squared. Now for x is larger than 1, of course, if x is larger than 1, then f prime of x is, well, this number is going to be, sorry, if x is larger than 2. If x is larger than 2, what happens? And we only care about the tail anyways, because these ends are always going towards infinity, so you can assume that after one point or another they're really, really large. So if x is larger than 2, this becomes 5 over 4, it becomes almost close to 1, and then it gets even worse. This becomes negligible. This goes to 0. So f prime is really, really close to 3. In particular, it's greater than 0. Now what happens when a first derivative is greater than 0? That means f was increasing, and that proves that you have monotone increasing, so long as for all n that are larger than or equal to 2. For all those, the tangent slope was equal to was positive, and back from Calc 1 you learned that whenever the first derivative is positive, your function is going uphill. This is a fancy way of proving that f prime, that the sequence is increasing, monotone. Nice, huh? Alright, I think that will do it for this word here. We're just trying to explain monotone. It's not the whole story. The whole story would be complete, well, not even part of the essential part of the story. There's more to the story because we need to see how this one plays into our ideas today for sequences in series, and that will be coming up in the next couple of videos. Alright, yeah, if you want to have something fun, prove that this one is monotone increasing. This is the same one that popped up last time where I said it would be fun to prove that it's bounded. If you did that and it was fun, you will love this one. Now prove that it is monotone. It's not that hard, actually. You can do it. Anyways, next video will explain why the magic happens when the function is both bounded and monotone. See you guys. Peace.